Hi, my name is Hughlin Reeves. I'm currently enrolled in FSU in the Computer Science Bachelor of Science degree program. I'm entering into my senior year, and I'm doing a presentation today on linear programming. First, we start with a little history of linear programming. It was began development in 1939 by Leonid Kantorovich, and then also George Danzig in 1947 picked it up, and some others involved in the developments were T.C. Koopmans and Frank Loren Hitchcock. What is linear programming? Linear programming is defined as a method to achieve the best outcome in a mathematical model whose requirements are represented by linear relationships. These linear relationships are often called inequalities. Linear programming is used for several applications. Some of the most common are to maximize profits, minimize costs, predict future home and business trends. It was used in the application of the Sudoku game, and more complex applications include quantum mechanics. There are 8 steps in linear programming. First, you want to read the problem, define the variables, find the objective function, then find the constraints. The constraints is going to be what gives you the boundaries on the graph. Then you'll graph the inequalities from the constraints, and then you'll find all the corner points. Test all the corner points with the objective function in order to answer the question. For example, a craftsman has 2 table designs that he can build. He can build one style of table that's made of knotty pine wood and another style that he makes of oak wood. The pine table can be constructed in 4 hours, and the labor and material costs come to $100. The oak table can be constructed in 4.8 hours, and the labor and material costs come to $163.20. He sells the pine tables for $185 each. The oak tables are $225 each. He's only given $1,200 each week to buy materials, and he only has 40 hours each week that he works. So how many kinds of tables should the craftsman build to maximize his profits? So we define the variables x and y now. We'll let x be the number of tables to be built, and x can be the number of pine tables to be built, and y will be the number of oak tables to be built. Now let's define the objective function. Since we know that each pine table is $185 and x represents the pine tables, and we know that each oak table costs $225 each, and y represents the oak tables, then we can find the objective function to be 185x plus 225y. This should answer our question. And now we're going to look for the constraints or the inequalities, and we're going to look back at the problem and identify everything that gives us the boundaries. We know that the pine table can be constructed in 4 hours. Labor costs come to $100. The oak table is constructed 4.8 hours for $163.20. We're only given $1,200 each week to buy materials, and we only have 40 hours each week to do the work. So this table kind of defines our constraints and inequalities, so that we can come up with some inequalities here. 100x plus 163.20y is less than or equal to 1200 as the constraint that we have on the money, is it costs $100 to manufacture the pine table, and $163.20 to manufacture the oak table, and we only have $1,200 total. Then the other inequality we have, the other constraint, is 4.0x plus 4.8y is less than or equal to 40, which represents we can make a pine table in 4 hours, and then we can make an oak table in 4.8 hours, and we only have 40 hours each week to do this. And then we also have the negative constraints. Obviously, we're not going to make a negative profit, a negative amount of money, so x will be greater than or equal to 0, and y will be greater than or equal to 0. All right, now we're going to graph the inequalities to find the feasible region. The feasible region is the area where, within the graph, within the 4 corner points that we're going to find. All right, and then so we're going to graph the lines 100x plus 163.20y is less than or equal to 1200, and the line 4.0x plus 4.8y is less than or equal to 40. In order to do this, we're going to have to find some points. So we'll let x be 0 and plug it in each formula to find the y values, and vice versa. Alright, and when we do this, we find that when x is 0 in the first equation, or first inequality rather, y will be 7.35, and when when y is 0 in the first inequality, x will be 12. Then in the second inequality, when x is 0, y will be 8.33, and when y is 0, x will be 10. And when we graph this, you see the darker shaded areas, which are right in this region here, and then at this point we turn and go this way. This is going to be the region that overlaps. This will be our feasible region. So somewhere in this area, one of these points will answer our question. Alright, now we're going to go ahead and do away with the points 12, 0, because it's way over here outside of the darker shaded region, and we'll do away with the point 0, 8.33, because it's way up here outside of the shaded area as well. So now we're going to find the other corner points, or find that this point right in here is what we need to find now. So that'll be basically our last corner point that we're unsure of. And we're going to solve this by elimination. If we take the second equation and multiply it by negative 25 all the way through, and it gives us negative 100x plus a negative 120y is less than or equal to negative 1000. Do the subtraction. The x's cancel, and we're left with y after the division comes to a 4.63, and so we know that y will be 4.63, and when we put that back into the equation and solve for x, we find that x is less than or equal to 4.44. And this graph was provided by Desmos.com, which is right here. We can put in the equation 100x plus 163.20y is less than or equal to 1200, and then we know that 4.0x plus 4.8y is less than or equal to 40, and that gives us the graph of both lines. If we include that x must be greater than or equal to 0, and that y must be greater than or equal to 0, then we see the region, and we can find this point, and that point right there is what we're most interested in. And again, this graph comes from the website Desmos.com. Okay, and it turns out that this that point right there, 4.44, 4.63 is what we determined through elimination, and it agrees with the graph. But finding these corner points, there are some problems with these points because we don't want to make a portion of a table. We want to either make a whole table or no table at all. So let's round up or down and stay within the constraints. In order to do that, we can either round the 7.35 can either be 0.7 or 0.8. And we do the test with the two inequalities. And 0.7, we see that it is true here. But 0.8 ends up being false because 1305 is not less than or equal to 1200. So then we know that 0.8 cannot be true because it did not stay in line with the constraints. So we'll have to leave that one at 0.7. Alright, the other corner points that are in question here that need to be whole numbers are 4.44 and 4.63. So they can either be 4.4, 4.5, 5.4, or 5.5. We can round each one of them either up or down. And then when we plug them into the inequalities to see if they stay within the constraints, we see that when we plug in 4.4, it ends up being true in the first inequality. 4.5 ends up being false in the first inequality, so 4.5 will not work. And then we plug in 5.4 in the first inequality and it's true. Plug in 5.5 in the first inequality and it's false. So our choices here so far are 4.4 or 5.4. And then we go to the other inequality and plug in the points. 4.4 ends up being true and 5.4 ends up being true, and since the other 2 points, which were 4.5 and 5.5, were not true or not met in the other constraints, we just throw them out. So we have the possibility of still 2 points here. We can either use 4.4 or 5.4. Since we're trying to maximize profits, we want to take the largest XY values that we can have, so we're going to stick with the 5.4. So now our table looks like the one in the lower right corner. We have 0.7, 10, 0, and the 0.54. And we'll also include the 0.00 because we know that x and y must be greater than or equal to 0. So now we can finally evaluate the objective function at the corner points. Remember, our objective function is 185x plus 225y. So we plug in these xy values and you see the results. 1575 for 0.7, 1850 is obviously the largest at the point 10, 0. Incidentally, I've created a very simple Java program that will find the minimum or maximum values. I'll just log into LinProg here. Alright, I'm going to go to the directory. Alright, and then on the left we have a shell open that shows a simple program. Forgive me, I should have had this logged in. Let me log into shell as well. change directories. Okay, and then we'll open with Emacs. Okay, here we go. I have defined some variables here. Then come down, we ask for the objective function coefficients. Then we ask how many corner points were obtained in the problem. And then we want to find out here on line 33 if we're looking for the minimum or the maximum. In this situation, we will be looking for the maximum. So then we'll go to case 2, which will give us the, I've got a for statement here for how many corner points we have. We're going to enter the X and Y values in, multiply them by the coefficients, and see which one has the maximum value. And so we'll do that over here in LinProg. I'm just going to run this program. Alright, enter the objective function coefficients. So we know that it was 185. And also 225. How many quarter points did you obtain? Well, we obtained 4 corner points. Enter 1 to find the minimum, enter 2 to find the maximum, and we're looking for the maximum, so I'll enter 2. Enter a set of corner points. Well, we know that 0, 0 was one of them. Obviously 0, 0 won't be the maximum. Next set of corner points, we'll enter it was 10 and 0. Another set of corner points was 0 and 7. And the last set of corner points was 5, 4. Alright, and this shows that the points on the graph maximum efficiency are 10, 0. With a value of $1,850, which is what we came up with here. 10, 0, $1,850. So lastly, we can answer the question. The maximum profit is $1,850 per 40-hour week, making 10 pound tables and 0 oak tables. I hope you have enjoyed this presentation on linear programming.